lecture, we talked about uh, treating a femboy or a person as a pendulum. So we vision them as a pendulum with a bob at the end, with the weight W, the length C for the rod. Okay. And then we have a displacement, angular displacement, theta, which is measured in radians, and it's a function of p. And we know that primarily it was governed by the equation theta double dot was g over w sine theta equals 0. But then we knew that for small theta, we knew that for small theta, okay, what we knew, and in fact, was that for all theta that is small, sine theta approximates theta. Sine theta is theta, or actually, I'm inclined to write it like this. So it's not precisely theta, but it approximates theta. And so, because of this fact, we're able to reduce this differential equation into theta double dot plus b squared theta equals 0, with b squared equals g over w. Okay, small news before continue the lecture further. On Monday, I believe the lecture is going to occur at my school. So expect a bigger board, maybe a better marker that I'm using, and maybe a little echo and maybe a little more silence, I believe. So I'm going to try my best to record there, and hopefully it goes well. So anyway, so this is what we talked about, and then we also likened this to oscillating behavior for any person, I suppose, like a gender fluid femboy. Right? So we attributed this and its solution, which is something in the form of sine kx or cosine kx, and then we attributed it to sort of behavioral fluctuation. So we liken this to the pendulum because we know that the pendulum oscillates back and forth between two extremes, and then this are equilibrium basically. So yeah, that was the last lecture. It was relatively short compared to our position theory lectures, but we tried. Okay. So we're about to end the course, and we're gonna end the course with a bang. And what better ways to discuss bangs, or explosions rather, than heat? Because heat is a byproduct of explosions, very rapid growth of heat, or very hard particles, or particles that's moving so fast. Because temperature is basically just a measure of how fast particles in a confined space are moving. So if your body's hot, like physically hot, not figuratively hot like sexy or something, what we mean is that the particles inside your skin or your body are moving so fast that they're generating heat. That they bump into each other and release energy in the form of heat. Now, what we want to do is think of a slab or a plate. Let's start with a plate. It's a metal plate that can conduct temperature. So, yeah, we have a plate, a metal plate that can conduct temperature, and so let's say that the part that's not shaded is cold and the part that's shaded is hot. Some critical threshold here. Okay, suppose that we froze time. Okay, time is at 0, it's not moving at all, so that the dx over dt or df over dt is sort of, it's 0 at the moment right now. So suppose we have a point over here, which is called P. P is point x, y, and then so we have our function, which is a function of x, y, and a time variable t. And so what this means basically, this y up over 1. This y describes, well, the heat at every point. So here, it's hot. So some hot temperature, or temperature that's near 100 degrees Celsius. I'm using Celsius, I'm not an imperial guy. I'm going to use imperial measurements. I'm going to use metric measurements here. So let's suppose that particles here, or near the far end here, are closer to 100. So this over here, this line, or particles that lie on this line, this P over here, P2, this P1, this here is 100 degrees, and this over here is 0 degrees, or P3. P1 is, or rather, well, F at P1 at time 0, or evaluated with time t equals 0, is let's say P1, let's say it's in the middle, right smack dab, so it's 50 degrees C, and then let's suppose that P2, or rather the function of P2 at our current time frame is t equals well, let's say 100 times 0 is 100 degrees Celsius, and the last, a function of P3 at our current time 0 is 0 degrees Celsius. So it's 150. Or rather, it's, you know, let's say it's actually 75. So yeah, 75. Say 75. This is actually 75 because it has to be hot, right? It's hot. 75. And then this one over here is the 50-degree mark. And then this over here, this P. Okay, so and then we have the P4 and then P5. So P4. So our function of f at P4. P4 with time 0, or 0 as our t variable, is 25 degrees Celsius, and then it's just this P5, the final point at t equals 0 is 0 degrees Celsius. So yeah, very, very cold here. So this is cold, very cold. And so there's some stuff in between. So there are points in between, right? So what can we say about this? What can we say about this? So of course, this part here is very hot. This part here is very cold. This one here is smack dab in the middle, so it's neither too hot nor cold. But in terms of degrees, you can say it's already quite hot for humans, I'd say. So now, if we imagine moving point 3 to point 4, right? And let's ignore time for the time being, or actually, yeah, let's say at t1, or t equals 1, point 1 moves to point 2, point 2 moves to point 3, and then so on and so forth. So point n moves to point n plus 1. So what happens to the heat, or what happens to the temperature? So now, instead of saying y, what I'm going to say is that f here is T for temperature. Okay? So it's T. So what happens to the temperature as we switch the points? Well, the temperature changes. So when we move point 1 to point 2, we get 75 degrees, or actually, for this one here, it's nothing now. So I guess point 5 here moves back to point 1. So point 5 now is 75 degrees. Point 3 is 100 degrees. Point 4 is 50 degrees, and point 5 is 25 degrees, or at least the position of it. And that happens in T1. You shift them, so they change stuff. So when we take a small nudge in this direction, or if we take a step in this direction in one of these points, say point 4. So point 4. Let's say we take a small, say dp 4. Let's take a small step in this direction. Of course, it's gonna get hotter as we move it, and then so in the same time, in order for us to actually describe that it changed, or that this over here changed, we're gonna need a corresponding dp. So now instead of saying dp4, we're gonna say d of f. D of f with respect to, well, of course, this direction, which is in the x direction. Okay. So this is the y-axis. This is the x-axis. Suppose that this corner over here is situated at the origin. So we're gonna assume that. So there's a nudge in this direction over here now with the df. Of course, there's no elevation change, so we only have that df over here. We just change our position here, and then at the same time it has an elapsed t here. So the total are given, or rather our temperature, or the rate of change of our temperature as we move P4 a certain df away from its original position. The measure of the change in the temperature is, well, as we move in this direction, well, in the x direction, is basically the partial derivative of t with respect to x. Change in temperature. As P4 moves to the left. And likewise, since it's moving this way, of course, it's getting higher. It's going higher and higher. So its slope, or change in temperature, is in a positive value, right? It's arbitrary though. The thing is, this is arbitrary. You can define it getting colder to be positive and it's getting hotter as negative slope. But here, let's say that if it's positive, it's going up. So that means the temperature is getting higher. So let's say this here gives a positive slope. So actually, what we're saying here is actually the change in temperature of T with respect to X. T with respect to X. Okay, so capital T, not small t. Okay, capital T with respect to X, evaluated at point P4. So we know its rate of change at this point, rather, or we know what its vector is, or where it's going, when we evaluate the partial derivative of this function with respect to X. And yeah, so it gives us the change in temperature, or how much the temperature changes as we move P4 a certain amount in this direction. Now if we move P4 upwards, so now we have another dF2. Okay. The thing is, when we shift it like this, the temperature stays constant because we only explicitly define temperature to change if we translate along the x-axis. We never said that, oh, this part is hotter than the middle, and the corners are hotter than the middle, or vice versa. We never said that. If we said that, then I guess this will be the same. This is cold but not very cold. So, and of course, it changes its temperature. It gets a lower slope as we go up. But in our case, we haven't defined that. So we just say that our d with respect to y, so our change in t with respect to y is 0 temperature. So there's no change in temperature as we make it go up and down, basically. So our slope remains constant every time we try to move point 4 up, or any of the other points actually. You can apply this to the part where it's heated. Now, let's think about what happens though if I let time flow and let the temperature or the particles move inside the slab. So we have this slab, of course. I'm going to erase these vectors, these tangent vectors, and we have our points. So let's say I allow the molecules that compose the slab to move. So molecules here are moving fast, molecules here are moving slow. So you guys know from the second law of thermodynamics that it always flows from hot to cold, never the reverse. The reason why this is the case because cold particles or particles are particles that move slowly. Okay, if your soup is cold, that means the particles in it are not moving fast, and since they exert less energy, they're not the ones that's overcoming the opposing particles here. It's the one with the larger energy that affects the one with the lower energy. You guys probably know it from physics. I'm gonna learn general physics, and that's probably gonna come up. So, anyways, yeah. So hot flows from hot to cold, but at the same time, since it's very cold here, it affects the hot particles here. They exchange energy. So at the same time, they sort of diffuse each other. So that's what's called diffusion. So two opposing sides meet each other and then they neutralize each other in some way. Okay? So this diffusion or neutralization of each other is governed by the heat equation. And it is a partial differential equation. So first I'm gonna tell you guys what the Dell operator is. So the Dell operator is this sort of vector-ish quantity. That's all the partial derivatives you can find from a function, or spatial partial derivatives. dz. And then so what we mostly do with the partial derivative, or this Dell operator, is take its dot product with our function to find out its basically rate of change with respect to the spatial dimension. So the rate of change of it going in this direction, the rate of change of it going in this direction, and the rate of change of it going in this direction. That's what we do when we take the dot product of this Dell operator with our function. So yeah, if we move it in this direction, that's just the dx. If we move it this direction, it's just the dx. If we move this direction, it's only dy. If we move this direction, it's only dz. But taking the sum of all of these guys is with some abstract vector, or it's some you can say resultant. So final sort of where the particle is going, right? So it's sort of a generalization. So if the particle is only moving in the x direction, you sort of say, okay, dy and dz are nothing. They're constants because we're only moving in the x direction, right? We're only moving horizontally. If it's dy, we're only moving up and down. So that means this and this are not, these two vectors are actually, they should give you something like a vector. So if you compute derivatives or something like the like, you're supposed to think of a vector, right? Of where the point is going to go next, or where the point is heading at, right? And so, right, going up and down. So it's not shifting left and right here. But suppose we have a dx and a dy, right? So if we take the dot product of the partial derivative with x and y, we get a sort of generalization or a end-all be-all function or derivative function for a multivariable function. So if we have a function that describes points in more than one spatial direction, this Dell operator basically gives us an end-all be-all derivative function that tells us, okay, even if we move one direction or in two directions or in three directions, we're able to know where the point is going just by adding them up. So adding up the vectors gives us a final vector which the point is actually moving in the direction. I know you can just identify where the point is actually moving, but suppose we're only given its direction in x, y, and z. Or rather, we're only given a function of its position with respect to x, y, and z, right? Like say this slab, which is only a function of x, y. We have a position here, right? And then they change. If we want to know what happens to the temperature as one point moves to the other, we definitely want to take this here. But since I defined this slab to only, I defined the change in the temperature of this slab to only be linear or to only be the x direction, it's mostly only going to be the d over dx over here. But anyway, back to the lecture, or back to the actual flow. What we do here is take its derivative with f. So we find the energies. And we do that by finding the energy of the function. We need to multiply it by some special constant called minus alpha, which is our heat transfer coefficient. It's given in your boundary conditions already, or if you have I suppose a boundary value problem or some predetermined conditions that you need to well consider when you solve the differential equation, and you're given the heat equation. I suppose the minus alpha part of the equation is already given. So what the heat equation basically states is that our energy, which is the heat coefficient, or the negative version of the heat coefficient, times the spatial derivatives rather, or all the sum of all spatial vectors, or all vectors acting on a point, or any possible vector, right, in our system, is equal to basically the rate of change in time. So the elapsing of time. So as time moves forward, it's just basically equivalent to some constant times any vector you can think of on the slab. No, it's very neat, right? So the function, or the equation, is in the form of d squared f, or t actually. No, actually it's just one variable. dt over dt is equal to minus alpha times the Laplacian squared of t. And now it's not the derivative to be precisely, or just the velocity. What we want are the acceleration vectors for any point on the slab, basically, or any point of, or any vectors in this t here, wherein t can be a two-dimensional, three-dimensional, or four-dimensional function. If it's a two-dimensional function, it's actually three-dimensional. If it's one-dimensional, like only a line or two rods, I suppose it's only just x, but it's still two dimensions because we have this t variable, wherein we describe every point or every temperature as a sort of position at a certain time frame, right? So this point here, before we shift or move these points to their the next ones, they have an initial temperature here. So as I defined, the P1 here is 75 degrees Celsius. So yeah, at this point P1, which is xy, an arbitrary xy here, so x direction here and y direction above, and when we have a specified time frame like 0, we're given a temperature. Okay, so 75 degrees. It's just basically minus alpha times the acceleration vectors of any point here. So if you want to move or shift points, is equal to the elapsing of time of this function. And so, okay, over here, this is called the Laplacian squared of t. So the Laplacian squared of t is basically just dt, d squared t, all second order partial derivatives of t, plus d squared t over dy squared plus d squared e over dz squared, and that's what it is. This is the heat equation that we keep talking about. This actually leads so much more to, this leads to so much more like Schrodinger's equation, which is a derivation of the wave equation, which is also a version of this equation. So if we assume some stuff like energies of a particle, and if, well, if we want to quantize it or quantize it, basically make it small, very small, we have to multiply by some I by h bar, you know, to make it a a quantum particle. Femmy physics is your time to shine. Clarify me on this. I'm mostly on the math. Okay. So yeah, how does this temperature stuff in slabs relate to our study of traps and femmos and gender fluid people that sometimes well dress as girls and sometimes dress as boys? Well, what if we are to sort of think of these states like male and female, or masculine and feminine, as basically like parts of the slab with some underlying abstract thing or emotion that's moving fast or moving slow. So if the emotion is moving fast, that means it wants to become a male, masculine, or it's actually arbitrary, but just follow me here. You can define it however way you want, but I want to make it this way. So if the motion is moving fast, that means that its temperature is high, right? and that means it's masculine. That's why it's up above. But I'm not saying that masculines are basically superior to feminines. I'm just saying that in our system here, since our males are in the positive zone, or the zone that's above, and then and our feminines on the below, just for the sake of comparison, to say to differentiate the both, not really to say that one's superior than the other. Okay. If it's now cold, if our particle or emotion is cold or more feminine, I'd say, the temperature is lower, and so it's down below. So now we think of some hypothetical slab or some abstract slab that describes the emotions of, or rather the inclination of a person during a certain time frame, t. So now we have ourselves our identity. So I is equal to some function of x, y, and t. So actually this is not x or y, but rather I want to say, I'd say p, just p and let's say a g for gender. So now our identity is a function of our inclination, or actually our inclination is a function of our gender at a certain time interval, right? And so now we can apply this principle with a slab, or actually a one-dimensional slab here. Okay, and then we have some like this. This is our P, this is our M, masculine, F, feminine. Just so that you guys don't think that M is up above and F is below, to get rid of superiority and inferiority complexes. Let's just imagine this is a top-down view. Okay. So M is on the left, F is on the right. I know it brings about other ideologies like leftist and rightist propaganda or stuff like or bullshit like that. But just think of them as like basically abstract things, okay? Then all these theories in these lectures are abstract after all. I made that perfectly clear in my position theory course. Okay, so M and F. So now let's say that, well, of course we have a slab here. At a certain time P, we have a certain inclination. Let's say this time here, we want to be masculine, this time here we want to be feminine, right? If we shift that point up to here, what's our corresponding change in our inclination? Our inclination, right? That is determined via the heat equation. Very neatly so. And likewise, if we use a two-dimensional slab analogy, like I said a while ago, or like I used a while ago, a two-dimensional slab analogy. Okay. Slab analogy like this. Here, and then let's say this hot region is the masculine zone, and then this cold region is the feminine zone. Again, we have some point. So now we have some two spatial dimensions here, two spatial dimensions. Some x and a y, so it's actually P, and then a gender identity here, or well, look at least. Man, the brightness is so high today. Okay, there. Basically there. And then now, if we shift points between each other, the change in temperature is determined by the Laplacian now. And then so the conduction of these guys, or the sort of stabilization, if we let it stabilize in a certain person, right? If we say let this stabilize, or say this is origin of one, this is the origin of the other, and then this is where they sort of go off to, right? These guys eventually cancel out each other and neutralize each other. And then that, my friends, or my students, is what we call behavioral diffusion. Behavioral diffusion is when we have two opposing sides or two polar opposites of a certain disposition or inclination, say masculine and feminine, and then if we let time go on, these two will eventually cancel each other out or stabilize to some compromise, like looking androgynous in public. And of course, it's determined via the heat equation. So, yeah. Actually, that's all there is to discuss about this thing, about behavioral diffusion. This is so there's actually another one here. It says conduction of confidence and doubt, and that's pretty much the same thing. So if we let the two polar opposites instead be confidence and doubt, so being confident that you're wearing this in public, and then like saying, oh, people are looking at me and I shouldn't do this again, like doubt. If we let them run their course, eventually they'll come to some compromise, right? Like say, well, I'm just gonna look and judge in public. They're not gonna judge me, and I get to feel confident about looking somewhat feminine but still looking masculine, and people will not judge me. So basically, your two states of mind come to some compromise at the end, and that does happen most of the time, right? You guys either become very confident, very doubtful, or come to some compromise, some gray area, right? So it cannot just be black and white, there's a gray area or overlap between the two. And that is exactly what we plan to model with this. So that's our application of this stuff to the topic here using our heat equation. So again, I'll write it down here. The heat equation. So I'm gonna get myself some markers. So again, our dt over our dt, so temperature with respect to time, is equal to sum minus alpha times the Laplacian square of our temperature function. And so, like that, we can translate it in terms of I now, inclination function. So we have a certain inclination I, so our di with respect to time is equal to sum minus alpha, which is some constant we derive from the. Well, you have some basically have some conditions or boundary conditions. You solve the differential equation, plug those guys in, and find minus alpha. Okay? That's pretty. That's actually pretty trivial to think about it. Because you can easily compute answers for this already. It doesn't matter about actually finding the solution to this differential equation. What matters is finding minus alpha here, which in our case is our behavioral diffusion constant. Now there's no precise measurement for minus alpha. It really depends on your boundary conditions and your solution. So that's Laplacian squared of I, where I is some function of our gender identity and time, or some f of g1, g2, blah blah blah. So it could be multiple guys or multiple genders depending on each other. So this gender here depends on this gender, and then the corresponding n gender is dependent on the n minus 1 gender. So that's our application of well, behavioral diffusion, or basically just diffusion into the study. And that concludes our course. It's been hell of a ride, but this is only the beginning of Regi Calculus actually. This is only the first part. Once you get into advanced Regi Calculus, you guys should be able to solve these guys with ease and also apply them to various things. But of course, do not dictate people with these kind of things, okay? I understand that differential equations have been a very important and monumental thing for humanity in terms of modeling stuff in real life, but you should not use this. You shouldn't use this to model stuff like or to dictate people's lives, okay? Like don't say, oh, because of what Professor Femmy said in his theory about differential equations, you should follow this because it's math. You should follow it. It's logic. It's solid. No, don't do that, because the human mind, if you think about it, is more complex than you think it is, okay? The human mind is much more complex than we think it is, and it cannot just be dictated or predicted by some scrappy equation that we develop out of logic, okay? Sometimes the mind of the human is out of logic or out of the lines of reasoning or logic at times. So yeah, and also if you try to dictate someone's life and well say, oh, you're gonna be like this tomorrow, they're gonna try their best to not be like that, to show that your model's wrong, okay? It's so a part of human psychology to disprove or discredit your model because of how you treat or how you use the model, okay? So for stuff that wouldn't change if you say that it's gonna act like this, okay, it's fine. So like we say rolling a ball on the floor, you make some differential equation about it, and then say, oh, it's gonna move in this position, or it's gonna move in this position after I roll it from here. Well, yes, because upon hearing that you're gonna say it's gonna roll here, And once you apply the adequate force for it to roll here, it's gonna roll there, without a doubt. But if you tell a person, hey, you're gonna identify as a female because according to some behavior you did, or because of your previous behavior, and because of this math equation, or solution to this differential equation that I was given, you're gonna be this tomorrow. Of course, they're not gonna be that because they want to make sure that this is wrong, that it does not line up with what they want. Because or they can follow it. I don't know. I don't care. What my point is, do not use this or my theories as a way of dictating other people's lives. Okay, that's the most important lesson to learn out of this course or in LOS in general. These are just basically hyperinflated jokes. Okay, these are jokes. These are not meant to be taken so seriously that you start being a jerk in public just because of it. Okay, I want to make that perfectly clear. That these things are abstract thought experiments, rather. Thought experiments for the sake of mathematical playfulness, or exercise, I suppose. It's another way for us to try to at least engage with those who are less connected with math, by sort of using math in contexts that they relate with, like the LGBT community. That's why I made these theories in the first place, to connect with you guys and teach you guys some math along the way. So make sure to please carry these lessons with you. Do not use my models or our lessons here in LOSC to attack other people. Okay, please do not do that. That's bad. That's generally a bad way to use my theories. The best way you can do this is play around with it and tell people, wow, can you check this out? This is amazing, and stuff like that. Don't tell them to be like this or be like that because your model said so. Okay? So that concludes this lecture. I suppose I'll be seeing you guys either tomorrow or on Saturday or Monday when I'm at my school. Expect better markers, of course. I'm gonna throw out these ones over here because they're pretty crap right now. So either Monday, tomorrow, or Saturday, I'm gonna be doing a lecture. If it's on Monday, or if I do a lecture on Monday, obviously gonna be at my school. Or at least I'm gonna try at least for it to be at my school. It could still happen here though. So 50-50 chance. Cross your fingers, I could do that, and we have a whole board at our disposal. So that's it for this lecture and for this course. I hope you guys enjoyed this course. Make sure to turn in your homeworks for me to grade, and basically good luck in your homework. So again, it's free to apply in LOSC, any course you guys want. You just need to subscribe to the channel and answer one of the many homeworks that I've given you guys for your designated course in order for you to enroll in the course. And so you're in. And then if you pass all the homeworks, then you got it. But I'm gonna need you guys to show your solutions for most of them, okay? But for abstract subjects like position theory, if I provide homework for them, I don't think I would require you guys to write down the proofs all the time, right? I think I would just rather you guys show the answer, but also like sort of explain your reasoning, but you don't need to write the entire proof. So that's it for this course, and I hope you guys enjoyed it, of course. And so I'll see you guys in the other course. So bye, see ya.